Hi everyone, we are Team Love to Work and we'll be presenting a final report on the project today. This is the roadmap that we'll be following throughout the presentation. And let's just begin with a quick overview of the question answering module, which derives its inspiration from transformers. Particularly, its basis lie in applying fine-tuned word framework to the task of answering questions in reference to the input passage. Thus, it more looks like the task of reading comprehensions. The key technical innovation in BERT is the application of bidirectional training of transformer to language modeling. Thus, it captures a deeper sense of language context and flow than single direction language models, and it can thereby achieve state of the art results across various reading comprehension datasets such as Stanford dataset version 1.1 and version 2.2. Um, this slide entails the architecture of the BERT, which is a multi-layer bidirectional transform. And the distinctive feature about its architecture is that it remains same across various tasks, whether it's for pre-training task or whether it's for any other downstream NLP task. The original English language BERT model was released into types. The first one was the BERT-based model, which had a 12-layer neural network architecture, while the BERT large model was a 24-layer based neural net. These are some of the more details that are used in training of the BERT, but since we used the pre-trained BERT model, we are gonna skip this. We used then the pre-trained BERT model and fine-tuned it on our Stanford data set so that it could be applied to the task of question answering, and the quality of the answers that were generated was human evaluated, and a small sample of the results is shown below, where the context or the passage and the questions were fed as a single input, and the answers were generated as the final output from the BERT framework. Next, I'll hand over to how to present.
Our question generator is a sequence-to-sequence model based on the T5 transformer. We utilized transfer learning, for which the model is first pre-trained on data-rich tasks before being fine-tuned on our question generation downstream task. Next slide. We chose the encoder-decoder architecture, for which the encoder is trained in a BERT style with a fully visible method, and the decoder is trained in a GPD style using castle approach. Next slide. The squat dataset is chosen for fine-tuning the question generator. For this task, the T5 is trained in a supervised manner. The model is fed the context and the associated questions for each context. We fine-tuned the model for 5 epochs using cross-entropy loss with stochastic gradient descent, and a scheduler is used for dynamic learning rate. Next slide. For model evaluation, the articles from the development data are fed as the input to the fine-tuned T5 model. The quality of the questions are human evaluated. The table below shows a subset of the results.
The novelty of approach we followed stems from the fact that the self-attention in BERT model significantly decreases the time it takes, also renders it diversity in task. Another fact is that the question answering module uses BERT while G5 uses T5, both of which can be downsized to be applied to any other NLP task without any major architectural change. Thus, this approach renders it more versatility in building a huge ecosystem of NLP-based objectives. Since we packed it on a Docker image, thus we ensured that any virtual or local machine can spin up a container, build the image, and successfully run the program. One of the main deviation from the proposed initial plan was to not use ErnieGen, but rather replace it with T5, which is the state-of-the-art result by Google. And the reason for the same was that ErnieGen could not be downstream for other tasks. Also, it was harder to use and was way too enormous in comparison to T5. Some of the challenges we faced were just coordinating, since we were across different time zones.
For our conclusion, we have shown that the Transformer-based fine-tuning techniques can be used for both question generation and question answering, using only pre-trained language models without the use of additional mechanism and extensive features. For our future work, we will propose implementing the quantitative evaluation metrics, for example, the BLUE, and also to train both the QA and QG models simultaneously to explicitly leverage their probabilistic correlations. And finally, for our reference,